Hi. So let's get started. So today I want to talk about uh, the second part of review, summation and recursion. Before I get to that, I want to uh, mention a couple of things. The first thing is that our class will start in person next week on Monday. You cannot be here in person. Please let me know. And if not, I would expect some of you to be here if you don't have any other circumstances. And I will try to make all the materials accessible online. Um, the second thing I want to talk about is the homework. So the homework has been uploaded, and it's always going to be uploaded on the class website. So you should be able to go to classwork page and click on homework one. So these are the questions that I would like for you to answer or to do in your homework. Um, the homework includes two types of two parts of assignments. One is the written part, the other is the programming part. So please take a look and let me know if you have any questions or concerns. Again, I will keep updating the homework, adding more questions after class each time. So I would suggest you to look at the homework and do them early, and ask me any questions that you have regarding the homework. Um, the other thing I want to mention is that the submission, so you can submit the homework to this email address following the submission format carefully. Again, I would like you to submit your homework to this email address, Gmail, so that we don't clutter all those people email when you email them directly. Um, So that's all I want to say. Actually, there's one more thing I want to mention. In terms of the when you're doing your homework, please show your already step. So make sure you're showing me all the work, like as much detail as possible, instead of just writing out the answers. Like for instance, for the second problem, you should be able to show me how do you get the answer that you say you're getting, right? And also question number three. Um, and again, please show all your work and let me know if you have any other questions. So having said this, today I want to continue our second part of the review. A lot of you might already know this. Today I want to talk about recursions and summations, and how can we use them to analyze algorithms. I will begin with telling you about some of the examples, and then I will tell you how we can use summations and to analyze non-recursive algorithms. And then I'll give you some examples that you can consider and you can think about at home. And then I will then move on to talk about how we can analyze algorithms in recursive algorithms using recursion, and then some examples. So I don't think I will be able to get the last two questions, the last two part today completely. So I will move on. I would move that to next class. So here's the first questions, first examples that we have. If you take a look at these functions, what does it do? What do you guys think? So here we have a function that takes in a list of numbers, right, an array of numbers, and is gonna do something, right? So if you look at this carefully, it's gonna look at the max value. Is gonna compute the maximum value from this of this input array, right? So for I equal to 1 to n minus 1, if this value a of I is greater than the maximum value, then the maximum value will be assigned to the AI value, and then at the end, the determination of the algorithms is going to return the maximum value. So given this algorithm, what do you think is the input size, and the time complexity of this algorithm? So last class, we talked about the inputs and the input size. You should be able to identify what they are in this case. They say I'm sharing the impulse. How do I do that? How do I? Yeah, it's kind of weird. Sorry. So my Zoom here skipped showing a few things. So if you look at the YouTube video, you should have the other component I talked about. But anyway, so this is the algorithms I want you to look at, and I want you to know, I want you to figure out what's the input and the input size and the time complexity. If you want to think about it, you can pause here. Otherwise, I'm gonna go over the answer. The input is the n numbers, right? That we talked about last time. The input size will be n, right? The array of n numbers. And what is the time complexity here? Well, the time complexity here, you need to identify the most basic operations of the algorithms. So here, what would be the most basic operations? Well, the most basic operation here will be the comparison. So if you look at the number of comparison being done, is roughly n minus 1, which is big O of n. So one of the questions that we want to answer today is, what is the mathematical way of measuring this complexity formally? And this is what we're going to talk about today. And this brings us to the ideas of summations and non-recursive algorithms. So if you look at the book, they provide a general plans for analyzing the efficiency complexity of a non-recursive algorithm. So there's 5 different steps. The first step is given an algorithm, you need to figure out what is the input size. So we talked about this last time, and then once you figure out the input size, then you have to figure out what will be the basic operations of the algorithms. A lot of time it will be the inner loops, right? A lot of time it will be some operations that you done repeatedly over time, over the duration of the algorithms. We talked about this last time, so you should be able to identify the basic operations. And then you check whether the number of times the basic operation is executed. So you want to, and then 4 is more about how do we sum up or create like a summation expressions that allows us to compute the number of times an algorithm is being executed. And then the last thing that we're going to do is that once you set up the sum, then you're going to use formula or basic summation rules to find a closed form solutions or the count of the algorithms. So as we said last time, if you do all of this, it gives you a good estimations on what the algorithms, the running times of algorithms. Having said this, so in the last couple of classes, I focused on 1 to 4. So today I'm going to focus on number 5. And let us look at some of the useful expressions that we saw earlier. I think most of you already seen something like this from your earlier discrete math classes. So the first formula basically says that the sum of the value that you sum over times a constant is equal to the constant times the sum of the numbers. For instance, I'm going to try to write on the board. Hopefully you'll be able to see it. So imagine that you have 3 numbers. A1 is equal to 1, A2 is equal to 2, A3 is equal to 5, maybe A4 is equal to 7. Can you see it? And then imagining a constant is like 100, right? Then what the first R1 is saying is that if you were to look at the sum of this constant C times AI, where I is equal to 1 to 4, which this is equal to when you sum up over I equal to 1 to 4, and you can factor out this AI out. So this is kind of fairly easy to see because you can expand these expressions, right? So this part becomes CA1 plus CA2 plus CA3 plus CA4, right? And then you get C, you can factor out. So you have A of C of A of 1 plus A of 2 plus A of 4, right? And now basically this becomes the C of AI, right? I equal to 1. So again, you can check manually if this is true. For R2, again, R2 is fairly straightforward. It basically says that if you have two sets of numbers, right, of the same index from L to U, then this is equal to breaking down the two parts, right, the sum of the individual parts. This is fairly straightforward. The plus or minus here is an expression where it is true when you have plus or minuses. So the book kind of abuses notation a little bit here. Let me change some markers. So what the book is very saying is that this is true. You have AI plus BI is equal to I equal to U, AI plus I equal 1 to U. Or this is AI minus BI. Okay. So that's what the plus or minus sign is saying. Again, this is fairly straightforward to show. I'm not going to do this here, but you can see this is true. There's also two identity that people use a lot of the time. For instance, the first one basically says that when you sum from I equal to L to upper bound U, and you sum over some kind of constants like 1 inside it, then this becomes the upper bound minus the lower bound L plus 1. So this is just basic counting here. And the second one that we're going to see pretty often in this class is this summation of I, where I is equal to 0 to n. Right? So basically, this says that the sum of I equal to 1 to n, then if you sum all of them up, then this is equal to n times n plus 1 over 2, which is 1/2 of n squared, roughly, which is big O of n squared. Again, the book was dropping the last term, but sometimes you might want to keep this just in case you want to do some additional arithmetic on it. Any other questions here? If you look at the appendix A of the book, it gave you a lot more of these inequalities to look at, or these identities. Okay, if you don't have any more questions, let me give you some example to look at. Again, if you're looking this from home, you should take a look at it and see if you're able to do them by yourself. So the first example is this one. So going back to the first algorithm that we looked at earlier today, this is an algorithm that finds the maximum elements of a given array A. If we let Cn to be the number of times comparison is executed, how do we count the number of Cn here? What's the right summation for this Cn? So for those of you that are at home looking at it, Cn again is the number of time comparison is executed, right? It's the basic operation. So we want to look at how many times this thing is being executed. And to auto construct the sum, you can look at the index I, which is from 1 to n minus 1 at 1. So we can set up a sum to be C of n, right? To be sum of I is equal to 1 to n minus 1. And how many time comparison is being done for each iteration? Well, so it's 1, right? Therefore, we have 1 here. Now, how do we solve this expression? Well, using the inequality that we saw earlier, right? The top part of this inequalities, this I, I equal to 1 to u is equal to u minus L plus 1. Then we can set this thing equal to, what do you guys think? Should be the top part n minus 1, right? And then u minus L, which is minus 1 plus 1. Right? The last two terms cancel out, so you have n minus 1. If I also written this in the PowerPoint, so you don't see this while I'm rolling on the board, you can also take a look at the PowerPoint. Right. Okay, so here's another example. We have, can you tell me what this thing is trying to do? So this algorithm basically takes an input of an array. It's gonna go from I equal to 0 to n minus 2, right? And then it's going from j equal to I plus 1 to n minus 1. And if ai is equal to aj, is return false. Right? Otherwise, it's going to return true. Right? So for those of you that maybe you want to think about what this thing is returning, and you can pause here. But for those of you that want to think about this, here is an algorithm that determines whether all the elements in arrays are different. Right? So this is not hard to see, because if there exists some elements that are the same in this array, then it's going to return false. Otherwise, it's going to return true, right? Because this statement will always going to be false. Now, what is the running time of this algorithm? So we want to count the number of time of comparison being made. In particular, we want to count what is the worst case, the inside part being called. So if you want to think about this, well, how do we construct Cn in this case? It turns out that Cn here going to be consists of two terms, two summations. The first summation will go from I equal to 0 to n minus 2. The second summation will go from j equal to I plus 1 to n minus 1. And then how many times does this operation happen within the loop? Well, it only occurs once. So now we need to solve this summation, right? So how do we solve this summation? So we're gonna unravel the inner term first because the inner term depends on I. What we're gonna do here is that we're gonna solve the inside term, which is what we used earlier, the formula that we used. So this part, inside term, we can say this is equal to n minus 1 minus this I plus 1. Okay, so I plus 1 plus 1. So what are you going to end up having here is that you have I equal to 0, n minus 2. You have n minus 1 minus I, because this part, the two part cancel out. Now we want to solve this. There's two ways we can solve this. The first way is that we can recognize this part. If you substitute 0, it goes from n minus 1 plus n minus 2 plus plus 1. I don't know if you can see this. Can you see this here? Okay. So this is let me rewrite this. This is n minus 1 plus n minus 2 plus plus 1. So what does this thing look like? Well, it looks like the formula that we have here on the top, right? So if we sum up the formula on the top, then you will have equal to this n minus 1 n over 2, right? Because n minus this is you summing up from n minus 1, which is the top part of this equation, right? So you substitute n minus 1 instead of n, and then you have n minus 1 times n over 2. So we good? Okay. So this is the first way of solving this. There's another way of solving it. Another way of solving it is to expand this whole term. So you have this term is equal to this whole term here is equal to the sum of each individual term, which is the sum of I equal to n minus 2 of n minus the sum of I equal to 1 to n minus 2 of 1 minus the sum of I equal to 1 n minus 2 of I. Okay, so we're just distributing it using the inequality that we using the difference of the sum, right? Formula that we have earlier. Now for each of the sum, we can solve this by applying the inequalities. So this part, because n and 1 is constants, so this becomes we can move the n out. So we have n times this n minus 2 minus 1 plus 1. So we have n, and then this is this is 0. Okay, so this is it'd be n minus 2 minus 0 plus 1, right? So this becomes n minus 1. So this becomes n minus 1, and this is plus n minus 1, because this is n minus 2 minus 0 plus 1, and then this part gonna be what we saw earlier, the sum of I equal to 0 to n minus 2, right? Which is, what do you think this would be? So applying the formula that we have on the top, we'll have n minus 2 n minus 1 over 2. Now we have, we can group this thing together. So we have n minus 1 squared minus n minus 2, n minus 1 over 2. We can distribute this term, or at least we can make it a common term and just divide them. So we have, this is 2 over 2. So we can combine the term together. So we have 2 of n squared minus 2n plus 1 on top, minus, when you distribute this term out, you have minus n squared minus 3n plus 2. So all of them divided by 2. Now the term inside, you have 2n squared minus n, so you have n squared left, right? And then you have 4 minus this part, which is plus, so you have minus n, and then the part inside cancel out. This is over 2, so you have n times n minus 1 over 2. So this is the same as what we got here. So there's 2 different ways you can express this.
The bottle.
Oh.
The bottle. The bottle. The bottle.
The bottom. Oh. Can you see this? So anyways, if you cannot see this, you can look at the YouTube video. So the YouTube video without my duration on this. Okay. And also, if you can also look at the slide. The slide basically provide the same duration. I just want to do it on the board so you can see it. And we have the same answer here. So our next example is about matrix multiplications. Here we are given a 2 n by n matrix C, A and B, and we want to find out a basic time complexity of computing the product of A and B using a very simple algorithms. For those of you that are at home or think about this, what do you think a natural algorithms for this matrix multiplication would be? If you want to think about it, you can pause here and just to somehow write out the pseudocode of the algorithms. So what would be the basic algorithm for solving this problem? Let me show you how to do this instead of writing it out. So we have an algorithm here, and the algorithm basically is gonna take input A and B. Like A is a matrix of n by n, and B is a matrix of n by n. And let's think about how we multiply two matrices together. Look at the entry of Cij. So this is equal to the value of Cij plus the product of Aik times this Bkj. Again, if you recall the problem we saw earlier, Cij, the entry of Cij is basically the sum of the elements products of the corresponding rows of I of A and J of B. So what we're gonna do at the end here is that we're gonna multiply this, the first entry, times the first entry of B here, and you're gonna sum all of the corresponding product of the entry, right, to get the entry of Cij. So this is what the for the inside loop is doing. So the inside loop basically says that the the value of the Cij is the sum of the coordinate-wise products of A of ik and B of kj. And the loop is going to go over every single elements in there from 0 to n minus 1, right? And then this will give you the value of Cij. But the thing is that you want to do this for every single entry of Cij. Therefore, you have two outer loops outside that basically compute every single entry of ik. So given this, what do you think the summation would be? Okay, what do you think the summation, the running time or the number of time this basic operation executed? One thing to note here is that what do you think the basic operation here will be? So you can count the number of multiplication or the number of addition. They should be the same regardless. So the basic operation is either the number of multiplication or the number of addition. Okay, so given that we know what the basic operation is here, how do we set up the sum to compute for this algorithm, or to compute the number of running time, or the number of times multiplication is executed in this code? Now we need to think about how we set up the sum, right? It turns out that this Cn can be set up in a very basic way by looking at the different for loop, by looking at the 3 for loops in the algorithms. So the first for loops goes from y equal to n minus 1. The second for loops goes from j equal to 1 to n minus 1. Right. And the last for loop goes from k from 0 to n minus 1, which is. Now, what we're going to do here is we're going to unravel each one of them, right? So now we're going to unravel the inside term first by applying the inequality we know earlier from the top. So we have what is this part going to give us? So this part is going to give us n minus 1 minus 0 plus 1, which is just n, right? This part gave us n. Now, because we can move the n out, and this will just give us like a 1 here, right? So we can further unravel this thing. Now we have this I equal to 0 to n minus 1 to n squared. And then we can solve this, and then this would give us n squared times n, essentially. Or so we have n. Okay. Again, you can look at the book or at least the slide to look at to understand how we get this. But this is the general idea. How much time do I have? Okay, so I have 15 more minutes. I want to go over some part of the recursion and some part of the some recursive algorithms. here's an example. I think we saw this last time. What do you think the algorithm do here? So you have an input, some output, right? And then you want to figure out what will be the basic operation here. For those of you looking at home, what do you think this thing would do? Well, I think we've seen some of this from last class. This is the input here. This is not hard to identify. The input is n. What would be the input size? As we said last time, the input size of a single number depends on the number of bit representation of that number. And the last part is, what is the time complexity? What is the basic operation? The basic operation here is either you can count the multiplication or the equal sign, but here we don't count the multiplication. Because multiplication is doing the same number of work as the equal sign, the comparison sign. Right? So either one is okay. So as I said, this is the answer. The value is n. The input size is the bit representation of that numbers. And so the running time of the algorithm, if looking in hindsight, is roughly n, because we're running this n times. But as I said before in the last class, we want to look at the time complexity with respect to the input size. So if we solve n, right? If we solve for the input size to respect to the if we solve for b, where the input size should be respect to the representation size, it turns out that the running time is actually big O of 2 to the b. Right? So it's exponential in the representation size. So this algorithm is not very efficient in general. Now the question here is how do we analyze this? How do we analyze this recursive algorithms? So today I want to go over some of the tools we can use to analyze the running time of these algorithms. In particularly, the book provided a general plan for analyzing the complexity of the recursive algorithms. First, they look at the parameters. So you have to figure out what will be the input parameters to your algorithm. And then you want to look at the basic operations, as we just did earlier. And then you want to set up the recursion or recurrence relations, which I hope you already know from last class, from the class we took last semester, 235H or 235. As well as deriving appropriate initial conditions, and then finally solve this recurrence relations. And then you look at what is the big O complexity with respect to this recurrence relations. So here's examples that I want to give you to see how we can derive recursions or recurrence relations for recurrence algorithms. So here's the examples that we had earlier that we saw for the computing factorials of particular input numbers. We're going to let n of n to be the number of times multiplication is executed. So for simplicity, we're going to look at n itself as an indicator of the algorithm's input size. We'll figure out later on the conversion later on, but here we're just counting the number of times the multiplication is going to happen, right? So how do we write out a recurrence relations for this? So if you remember from your 235 class, you need to think about the total number of time you run, right? Depends on the number of times the algorithm runs before the step before you, right? Plus the number of time the operation is performed when you are in each of the instance sizes. So this will be plus 1. And we also need the initial condition. So what the initial condition here will be? Well, the initial condition here will be n equal to 0, right? Because when n equal to 0, you don't do anything. You don't do any multiplication. You don't do any multiplications. In particular, this is the recurrence relation. I'm going to just show you this. Now, given this recurrent relations, how do we solve this? Do you all remember how to solve this? So the most basic way of doing this is substitute in. So you can keep substituting in. And write down the base case and look at the pattern that you've seen earlier. So we can do substitution. So here we can start out with saying, I don't know why they're running off. So you have m of m is equal to m of n minus 1 plus 1. You can substitute this one in, right? So this becomes n of n minus 2 plus 1, right? Because I'm substituting in, and I'm getting this thing back, plus 1. And then what I can do here is that I can further substitute in n minus 2, so I have n minus 3 plus 1 plus 1, which is what I have n plus 1. Right? So you can see the pattern where you have m of n minus I plus I. Right? Now I can substitute in when I equal to, I don't know why they keep running out of. Right. Now I can substitute in I to the n so that I can get the base condition to solve this one. So I can say I'm gonna let I equal to n. Then I will have m of 0 plus n, right? Because this part is 0, I have n. Right? So the basic method of solving recurrence relation is to do substitution. So you substitute in the answer until you find a pattern where you can substitute in the basic base conditions to get rid of your base term at the end. Here's another way of solving this in the PowerPoint. Again, if you don't follow what I wrote here, you can also follow what I have in the PowerPoint. Okay. So I only have 5 minutes left. I want to go over this PowerPoint on, but I want to save it for next class. So just to conclude today's class, I want to remind you that we have a class next week in person. If you cannot come again, let me know, and then I will figure out some alternative for you. Again, all the video lectures gonna be uploaded online. And then I will go over the next class, but sorry, let me just skip all of them for now. And then in the next class, I will be doing a survey in class, or if you're online, you will be doing online. So this is a survey that I have done last semester, or is not conducted by me, it's conducted by other faculty in the department. So what they want to do here is that they want to look at how to improve first year experience, how to improve the first year CS courses, and they want to survey you some questions about the classes that you have took in previous year about your experiences. It has nothing to do with this class. It's just that they want to survey some of you. So we're gonna take 20 to 25 minutes of our next class to answer these type of survey. And then there's other demographic information, but all these information will be anonymous, so you will not be identified. Um, Also, next class I will also use some of the time to address any questions of concern. And we're not gonna do a lot other than going over the remaining part of the versions, introduction materials. So that's it for today. I mean, that's all I have.